Yes, I'd like to say something.
Oh yeah, right. I should say that I asked explicitly whether Professor Schmid minds being asked questions during the lecture, and the answer was no. So try to maximize your understanding by asking reasonable questions if you're there. Well, pretty sure. So we try to keep it as informal as possible. Okay, well.
All right, so 3 lectures. The first one I will talk about and I will describe generalities of representations in reductive groups. Second lecture, a quick summary of the relevant facts in Hodge theory. And then the third lecture we'll put the two together. So let me start out by looking at G sub R. So that in some sense is the group of interest. So it will be a connected linear reductive group. And so, of course, linear means that it can be realized as a group of matrices, and then reductive. So what does reductive mean? Well, I don't give you a characterization that is not the definition, but it's certainly a good working definition. So reductive means that it is first of all an algebraic group. So linear means it's a group of matrices, so when you realize this group of matrices, an algebraic group means defined by a set of polynomials plus an additional property that you will see in just a moment. So KR in GR will be a maximal compact subgroup. And it is unique up to conicacy. So that is a general fact. And since these are algebraic groups, it makes sense to talk about the complexifications. So let's say GR is a group of real matrices defined by the vanishing of some polynomials with real coefficients. And of course, then you can look at all complex matrices that satisfy those conditions. That's the complexification. And then I choose UR in G. So G is the complexification of GR. UR in G a compact real form. So, compact Lie group that sits inside G the way Rn sits in Cn. And then the characterization of reductive is the existence of such a compact real form. So one way to say that is that being reductive does not change under extension of scalars, and compact groups are reductive. So that's then a working definition of being reductive. And let's say one family of examples that you might keep in mind would be GR, UPQ. So the group of matrices that leave invariant, complex matrices that leave invariant a Hermitian form with a P positive, Q negative eigenvalues. And of course I want to think of it as a group of real matrices, which is of course possible. And in that case, KR would be U of P plus U of Q. And G would be GL P plus Q C. K would be GL P cross GLQ, and UR would be U P plus Q. So, as general notation, I will denote the Lie algebras by GR, KR, G, K, and UR. Okay, so that is the general setup. And so then I will look at representations. So let's say I V a representation of GR. And so here V is a complete locally convex output topological vector space defined over C. So there is, one needs to require continuity, of course, otherwise there would be no connection with the Lie group structure. So it is continuous in the sense that the action map from GR plus V to V, so say the map induced by pi is continuous. And let's say a very important special case would be that V is Hilbert space, and pi of G for G and G is a unitary operator. So, what I should say is that, well, let's say unitary representations, those are the building blocks of harmonic analysis, and of course they have intrinsic importance. And then what was realized very early on by Harishchandra is that even if you are primarily interested in this case, it still makes sense, and in some sense it's even necessary to consider the more general situation of representations on deep, locally convex Hausdorff topological vector spaces. And you may wonder why that class of vector spaces. And the answer is that it makes sense to integrate functions with values in such vector spaces. And that is being able to integrate is one of the important tools, so this is why this is the important class of representations to consider. Again, of primary interest are unitary representations, so of course, that means that it is a unitary representation. And, but as I said before, it makes sense to look at this more general context. And so then terminology, so pi is irreducible if it does not exist a non-trivial closed invariant subspace. And the word closed is important because for irreducible representations that typically exist lots of non-trivial invariant subspaces, it's just being enclosed that makes it much more restrictive. And then one says that pi is finite length. If every chain of nested closed invariant subspaces is finite. And then finally, pi is admissible if pi is equal to kr. So this is now a representation of a compact D group, and the reducible representations of compact D groups are automatically finite dimensional. So pi restricted to kr breaks up the form of this. So each irreducible representation of kr occurs only finitely often in the restriction of pi to kr. So then a basic fact we should have Chandra is that the irreducible unitary implies admissible. So, vaguely speaking, if one looks at, for example, representations in this general context, which are of finite length and admissible, that in some sense is the class of representations to consider. And then in this class we have the irreducible unitary representations that we are particularly interested in. Now, in the finite dimensional case, if you have a finite dimensional continuous representation of a new group, it's automatically C infinity and even real analytic. So, in the case of finite dimensional representations, one gets obviously a representation of the algebra, and the representation of the algebra knows everything about the representation of the group except questions having to do with connectedness and coverings. So in the infinite dimensional case, well, in general, I mean, there are various ways in which one can try to get the notion of an infinitesimal representation. But in fact, the only situation where this works really well is the setting of reductive groups. And so this construction, of course, is due to Hodge. So let me define HC for Hodge of V. So V is now a representation on a complete local convex Hausdorff space, and so pi should be admissible of finite length. So those are the standing assumptions. And then Hodge of V is the linear span of all finite dimensional KR invariant subspaces. So that it turns out, and of course all of this is due to Hodge, that HC of V is dense in V. It consists of C infinity vectors, meaning that if I send G to IGD, that this is C infinity now from the group to the vector space. So V consists of C infinity vectors. So V is C infinity if the map from G to pi of G is a C infinity map from the group to the vector space. And So it consists of C infinity vectors, which are even weakly analytic. So what does that mean? So if I have a vector, what would it mean that E is weakly analytic? Well, this is, the vector space is complete locally convex Hausdorff. It really doesn't make sense to talk about analytic functions with values in such a vector space. But what does make sense is to pair, so now suppose V is a vector in the space. If you look at this function, it is a priori a continuous function, because pi is supposed to be continuous. So it is a continuous function, and therefore, if you pair it against a vector in the topological dual space, you get a continuous scalar function. And weakly analytic means that those functions, meaning g goes to pi of g, evaluated on a vector in the dual space, and those are real analytic. And so, of course, among these we have Banach spaces, and then it turns out that when V is a Banach space, weakly analytic implies analytic in the usual sense. But from the point of view of actually proving facts about such representations, what is crucial is that Qaisar of V consists of C infinity weakly analytic vectors. And so this implies that, well, K and G act on HCV. So what does this mean? Well, you know, by definition, KR acts on HCV. It's the linear span of all finite dimensional KR invariant subspaces. And if you have, so it's exhausted by finite dimensional representations of KR. And on any finite dimensional representation of KR, you have K active. So K acts naturally because of the definition, and G acts because these are C infinity vectors, and in fact, weakly analytic vectors. So they both act, and they act compatibly. So what does it mean for the actions to be compatible? Well, the Lie algebra of K is German K, which is a sub-algebra of German G. And of course, by differentiation, the action of the group K is an action of the algebra K, and then both G and K, well, so K as a sub-algebra of G acts, and of course the two actions by differentiation and action as a sub-algebra of G coincide. That's what it means for the actions to be compatible. And the fact that we have these compatible actions are referred to by saying that HCV is a GK model. So GK module means we have an algebraic action of K, an action of the algebra, and the two are compatible in this sense. And so then the real analyticity implies that V goes to HCV is a faithful functor, and HCV is irreducible if and only if pi is irreducible. So in that, what matters is the weak analyticity. Basically, what this reflects is the fact that the function g goes to pi of g for a vector in hc of v.
Is there anything tricky because hc of v is not complete?
No.
No,
I mean, so again, I mean, we can look at these functions, and since our Chandra V consists of C infinity vectors, these are C infinity functions with values in a good topological vector space. It's just Chandra V is not the topological vector space, but that doesn't matter. These functions take values in a good topological vector space. And then the weak analyticity matters because a weakly analytic function is determined, I mean, on a connected space, is determined by its Taylor series at a point. And of course, the Taylor series is characterized by the action of the algebra. So without weak analyticity, you could not possibly conclude something of this sort. And so there is, let me say this slightly more formally. So under this standing assumption, so I assume this, HC of V is finitely generated over the universal Delphi algebra of V. If one has a representation of the algebra, then of course the representation space has the structure of a module of a universal Delphi algebra. So it is finitely generated over mu of G. That is a reflection of the finite length property, and it is admissible as representation of K. So it's a GK module. K acts by an algebraic action, and well, I already said that Harshchandra of V is admissible as a representation of K, and of course it is a GK module, and these are the characterizing properties of a Harshchandra module. So a Harshchandra module is a GK module finitely generated over U of G, which is admissible as K module. And so then Harshchandra is a functor from representations which are admissible of finite length on such topological vector spaces to the category of Harshchandra modules. Now, it may be helpful to look at an example, and this will be a recurring example. So, I will look at GR, which will be SU11. So this is the group of matrices determinant 1, the invariant Hermitian form of signature 1,1. And then explicitly this means that one looks at all matrices alpha, beta, beta, alpha, with alpha, beta, complex numbers, such that the determinant is 1. And KR, what is KR? Well, again, KR is determined only after conjugacy, but the obvious choice would be the diagonal matrices of this form. So alpha 0, 0, alpha inverse with alpha complex and absolute value alpha equal to 1. And then G would be SL2C. And K would be the group of all matrices alpha 0, 0, alpha inverse with alpha in C star. So K is in fact, as you do, isomorphic to C star. And then U R will be SUP.
Wilfried, the formula for KR, have you got an extra conjugation that you don't need?
The absolute value 1.
That you have alpha and alpha bar
I
now?
mean, that's the minus, that's the minus 1.
For minus 1.
Right. So, yeah, so those are the groups in this particular case. And of course then G acts transitively on complex projective one space, which I think of as the complex plane compactified by adding the part of infinity, and it acts by linear fractional transformations. And GR and KR are, well, so this action G of SL to C, of course, is transitive. And GR and KR, as subgroups of G, also act, and these act with 3 orbits. In the case of GR, those 3 orbits are the unit disk, the boundary of the unit disk in C, and the complement of the closure of the unit disk. And KR acts with orbits 0, C star, and the point of infinity. Now, what I should have said in the beginning is that up to conjugacy inside G, SU11 is also SL2R. And we typically are more familiar with SL2R with SU11. It's really the same rule. And the reason when I look at SU11 rather than SL2R is precisely that the description of the orbits is slightly simpler. The action of K is simpler. I mean, simpler to describe. It's a linear action. So then, it may strike you that both numbers are 3. And not only are they both 3, but there seems to be some connection between the orbits. And this is not an accident, as we'll see. This is a general fact for groups in this setup. So we will see the general version of this picture in just a moment. Well, not just a moment, probably in the third lecture. So, now, I want to describe.
Is this Qaisar or KC?
That is what KC. K. Then that will form. And then K. So, of course, K is really C star. And how does K act on C? It acts on C by sending A, by A acting as multiplication by A squared, because it's a linear fractional transformation. And you see the A and then the A inverse in the denominator and make an A squared. Alright, so let now the space of polymetric functions on the unit disk, and apologize by locally uniform convergence. So that makes it a complete local convex Hausdorff space. And so GR acts on delta and hence on V. And it's easy to see that this action is continuous. So we get a representation. So is the resulting representation is it irreducible? Is it of finite length? admissible. So let me ask you, when you does not include people like Dragan or Greg. So is this representation irreducible? Do they exist closed in area subspaces?
Constant.
The constant. So the answer is no. C indeed is closed in area. But then it's not difficult to show, and it's pretty obvious, that C, so the answer here is yes, because C is the only non-trivial closed invariant subspace. So it does have finite length. And is it admissible? Well, the answer here is yes. And so the point is that if I look at z to the n, so this is k invariant, and if I take a in k, which I identify with c star, acts on z to the n. How does it act? A acts by multiplication a squared, so what does it act on z to the n? A to the 2n? How can this be? It's a to the minus 2n, and why is that? Yes, because an action on the space and an action on the function. The action on the space is covariant, the action on the functions is contravariant, so we have to put it in. Well, that's just a minor remark. Okay, so it acts by a to the n, and this is the only such subspace. Meaning, if I look at any subspace where a acts by a to the 2 minus 2n, by a to the minus 2n, it is that subspace, there's no other. So yes, it's admissible. Each irreducible representation of K occurs either once or not at all, depending on the parity and sign of it. And so what is HC of B? Well, it's the linear span of z to the n for n positive. So this is the space of polynomials on where? Well, I should think of it as a space as delta, unit disk, and polynomial makes sense on all of C. So the space of polynomial functions. So this is, just a very simple example where you see a lot of these phenomena being admissible or finite, not irreducible. That's the Harsh-Chandra module, and obviously on the Harsh-Chandra module, the algebra acts by differentiating linear fractional transformations generated one-parameter groups, generated by elements of the algebra. So this then is a Harsh-Chandra module with an obvious action of K, there we see it, and in the algebra, differentiation. Well, maybe I should have done this in the opposite order. So, yes, so now suppose well, for general G, that pi d is irreducible unitary. So D is a unitary transformations. So as I said before, that then means automatically that the representation is admissible. Yes, by the way, before I do that, I should comment slightly more on what I said over there in the case of this example. I won't write down the statements because that would take too long. But so here we have the Harshchandra model. So the space of polynomials with a definite action of G algebra G, group K. And so you might ask, do there exist other representations that have the same Harshchandra module but are in some sense different? That's the answer. Well, there's some obvious representations that on complete locally convex Hausdorff spaces that have the same space of k-finite vectors. How about holomorphic functions with C-infinity boundary values? Holomorphic functions with LP boundary values for p between 1 and infinity. So all of these are complete locally convex and the action of G is continuous. So typically each Harshchandra module comes from an infinite number of irreducible, admissible representations if the Harshchandra module is irreducible. And really what it means is that all of these representations are basically the same, except for the choice of the form. And so I should mention the terminology of the infinitesimal equivalent. That means same Harshchandra model. And then an important fact is irreducible. So for irreducible unitary representations, infinitesimal equivalence implies unitary equivalence. So, in the general case, having the Harshchandra module means, well, the representation from which it comes, there's some freedom in how to topologize, but in the irreducible unitary case, there is no freedom, and you will see in a moment why that should be. So for irreducible unitary representations, the Harshchandra module really determines that irreducible unitary representation. So IV is irreducible unitary, and then by restriction, HC of E inherits a GR invariant in a product. HC of E physically sits inside this derivative. And so you can restrict the inner product. And then, well, the fact that GR acts unitarily means that when you differentiate, you get infinitesimal invariance under the Young. Okay, so by restriction, Harshchandra inherits a GR invariant in our product. And so that is the explanation for this fact. Namely, you take this, if you have an irreducible Harshchandra module, with GR invariant inner product, you just take the global space closure, but then some work is to be done, namely that the infinitesimal action lifts to an action of the group. If it does, then action will be unitary because its derivative is preserved by GR. So Harichandra proved that. So let me now state the general facts. So determining the irreducible unitary representations comes down to 3 parts. A, describe all irreducible rectangular models. And that's been done. And I will explain in the third lecture one way of doing that, maybe the best way of doing that. And then problem B is determine, so it's been done, and this was done 30 years ago, and the answer is quite nice, but it's not trivial. I mean, some work actually has to be done. But it's well understood, so it's been done and well understood. Problem B is to determine which of these, meaning irreducible rectangular modules, carry a non-trivial GR invariant Hermitian form. And so this is easy and is really formal. To have a Hermitian form really means that the representation is isomorphic to its conjugate dual. And you just translate into what that means in terms of the solution of this problem. So this is really a formal step, and there is nothing particularly different about it. But then the third is, yes, I should say that this is unique up to scaling. If it exists. That is some form of Schur's lemma. Right? I mean, when you have finite dimensional representations, and when they're irreducible, then an invariant product, if it exists, is unique up to scaling. You prove this by Schur's lemma. Schur's lemma is a statement about finite dimensional representation. So how does it apply to the Harichandra modules? Well, it applies to Harichandra modules because in the background there's something finite dimensional, namely the space of KR finite vectors, which are, that's a union of finite dimensional subspaces, and by doing arguments properly, cleverly, you can apply Schur's lemma even in the context of these infinite dimensional vector spaces. So the Hermitian form, when it exists, is unique, and then problem C is determine which of these invariant Hermitian forms are positive or negative definite. And so this is in some sense the crux of the matter, right? To determine when So when you have one of these, and that's pretty easy to tell, whether or not it's positive or negative. And of course, the fact that this is a difficult problem means, well, having this Hermitian form, this GR Hermitian form when it exists, I mean, you see it for some formal reasons. You don't see it as an explicit Hermitian form. And since you don't see it as an explicit Hermitian form, it's not obvious whether it's positive, definite, or not. So that is really the remaining problem. And I should say that, the problem in this sense may be without totally explicit description. This was all understood by Hodge. So the problem in this form has existed for quite some time. Now, as part of these lectures, I should give you at least some example of representative representation. So let me do this here. So for energy, the L11 over P1, seeming in infinity, the polymorphic line bundle of degree n. So what does degree n mean? Well, such a line bundle has a Chern class, and the Chern class is then a multiple of the generator of H2 of P1 with integral coefficients. So there's an obvious integral invariant, and then it is unique. That is, up to isomorphism, there exists only one line bundle of degree n on Pn, on P1. And it is, or I should say, can be made on G. So, for example, for n positive, one can think of the space of sections as being polynomials on C2 that are homogeneous of degree n, and then G acts just because G acts on C2 and therefore on polynomials of C2. So G acts, and now GR, in this particular case, if I take GR or KR, that is SU11 modulo the diagonal groups, it's easy to see that that can be identified with the unit disk. And since, GR acts transitively on the disk with compact isotropic groups, so that implies that both L of n has a line bundle over the unit disk, and delta carry the R invariant metrics. And they are unique up to scaling. Right? Because if you want to construct something GR invariant on a space that GR acts on transitively, we have to construct it at a single point, and if it's invariant under the action of the isotropic group at that point, we can then transfer it around. So that's the idea. And so the line bundle restricted to the identity coset is just a complex, it's just a copy of C. And so there is a unique Hermitian metric on this one-dimensional vector space, which is invariant and scaling. I mean, obviously, we need one. And similarly for the tangent function, so both carry invariant metrics. And therefore, so if I look at H2 delta Ln, by which I mean the space of L2 holomorphic sections on delta. This is the Hilbert space, or zero. So that's certainly possible. And GR acts on it by, well, so of course, this means holomorphic sections that are square integral with respect to these invariant metrics. And if the metrics are invariant, that means that the inner product is invariant, so it acts by unitary operators. So, as a result, even for essentially formal reasons, what we get is a unitary representation, but it might be zero. And so then, in this, I guess the person who first formally stated this was Bartman in 49, and the first really significant paper in this subject showed that H2 of delta Ln is not equal to zero if and only if n is less than or equal to minus 2. And the resulting unitary representation is irreducible. And then let me continue without writing this down. So by looking at these representations, so for n less than or equal to minus 2, we get a bunch of reducible unitary representations, and of course we can look at their duals. And by the way, what are they? So remember that GR acts with 3 orbits, namely the unit disk, the boundary, which clearly looks different, and then the complement of the closed unit disk in P1. And of course you can do the same thing for the complement. And so those representations, for pretty formal reasons, are dual to these. So if I look at these together with their duals, they constitute the so-called discrete series of SU11. And the discrete series, that is the class of irreducible unitary representations that occur inside L2 of GR. So the discrete series of SU11 consists of these representations and their dual. By the way, before I gave the example of just functions on the unit disk, and then I said, well, there are various ways of getting the same higher-channel module. One is holomorphic functions on the disk with L2 boundary values. Is that a unitary representation? This is an example. Well, the answer is no. And the answer is no because, so rotation, meaning KR, certainly acts unitarily. But if you take a linear functional transformation that is, for example, that corresponds under the isomorphism between SL2R and SU11 to stretching, that will not act unitarily. And of course, it couldn't be unitary because the complex numbers are an invariant subspace, but the only invariant subspace. And if it were unitary, the orthogonal complement would also be invariant, but it is not. Okay.
That's saying our Shanghai numbers.
Yeah. No.
I mean, the numbers are the same. They are relative boundary.
Yes, that's right.
So, but and you said, and by the uniqueness theorem,
No, but I'm saying, well, yes, so so
abstract.
L2 boundary values, that does not mean that you have a unitary representation. But these are obvious unitary representations for this group. And they are distinguished in the sense that they occur discretely in L2. So that is the discrete series. Okay, so I have just a little longer. And so let me start the following statements that So I want to at least state one reduction of this set of problems. So as I say, where is it? The problems that I listed before. So describing the irreducible Hodge-Lambda modules, determining which carry GI and value definition forms, and then to determine when the initial form is positive definite, and as I said, that is the approximate amount. So, but for these problems, there is a well understood reduction, which is some years back, which I want to describe. Okay, so there is so an important reduction of problem C. So suppose M is an irreducible and let Z of G, the center of U of G. So it turns out that that is a polynomial algebra over C. And so this acts on M, well, because U of G acts on M. And as I said, that in the context of Hodge-Lambda modules, one can, when arguing appropriately, apply Schur's lemma, and so it acts on M by a character, because I'm assuming that M is irreducible. So then the set of the universal enveloping algebra acts by a character. So character meaning a homomorphism of the algebra over C, Z of G into C. And that's called the infinitesimal character of I. And so, so this is a long time ago. Bogan argued that it suffices to consider the case and let me put this in quotation marks because I have to tell you what it means. So what I'm writing down now has no obvious meaning. I will have to explain. It acts by a real infinitesimal character. And so, as I say, I will explain what that means, but let's suppose you accept that for the moment. So, what does the reduction amount to? Well, if you have a general irreducible unitary representation, then it can be obtained by parabolic induction, which remains irreducible, so by parabolic induction from a representation of a subgroup, which does have real infinitesimal character, and the induction process is irreducible, unitary, and totally transparent. So if you have an irreducible Hodge-Chandra module that is at least a candidate for being unitarizable, in the sense that it carries an invariant Hermitian form, then you can tell from what representation with real infinitesimal character is induced. And then you look at that representation of the subgroup and see whether it's unitary or not. That's the nature of the reduction. Okay, and so let me say just the beginning of the definition. So I will use 5 minutes to give you the beginning of the definition, but the completion of the definition will probably come in the third lecture. So, yeah. So let H in G. So G is the complexified group. Be a countdown subgroup. And what does that mean? In other words, a subgroup isomorphic to C star to the R, isomorphic to C star to the R as algebraic subgroup of G with R maximum. So that is a perfectly good definition, right? We're looking at algebraic subgroups that are of the form C star to the N, to the R, and then with R maximal. And if you have it, then that's a compound subgroup. And it obviously exists and is unique up to chronicles. Let me remark that one also has the notion of a compound subgroup of GR, and a quick way to define that is a Lie subgroup whose complexification, algebraically subgroup, whose complexification is a Cartan of the complexified group. And then the statement that it's unique up to conjugacy in the real context is not true. And so C is algebraic complete, R is not. So in the context of GR, compound subgroups can be defined by complexifying, and then there will be finitely many up to conjugacy. So I can assume that this compound subgroup comes by complexification of a compound subgroup from the real group, but it doesn't matter. Okay, so I have a compound subgroup, and then that means that H, the algebra, is isomorphic to C to the R. It's an Euclidean subalgebra of G of dimension R. And I need to look at the value. So the value is the normalizer in G of H, and of H. So this is a finite group. And since H is abelian, well, the normalizer of G in H acts on the group H, so it acts. And what is not completely obvious, but not difficult either, it acts faithfully, of course, on H, on computation. And if it acts on H, it acts on its the algebra, and then by duality it acts on the dual of the algebra. So, a very early result of our genre is that there exists a natural and easy to describe isomorphism between the center of the universal developing algebra and the symmetric algebra of H in there the violent invariants. Right, so you look at the symmetric algebra of H, the Bargroup acts, since it acts on the German H, and you take the invariance, that is the center of the universal developing algebra. And then there are well-known algebraic results which say that this is a polynomial algebra over C. And so therefore, for each lambda in H star, there exists a character Qaisar I lambda from the center of the universal development algebra to C, which is evaluation at lambda. Namely, you think of this as being that, and then the symmetric algebra of H can be thought of as being polynomial functions on H star, violent invariant polynomial functions on H star, so you can evaluate it at any lambda. And so then, so all of this is Harshanga. Chi lambda is equal to chi u, if and only if lambda is WU for some W and W. And then to finish the story, every character of C, character meaning homomorphism to C, is of this form. And so, the infinitesimal character in the reduced linear shadow model is therefore of the form chi lambda, with lambda in H star but determined only after the action of the model. And so, real infinitesimal character means that lambda lies in a certain real subspace. And what is this real subspace? Well, let me say it in words, but I will say it more precisely, maybe not more precisely, but much more transparently, understandably in the third entry. So in H star, there is a natural lattice. What is this lattice? So if I look at the homomorphisms of algebraic groups, from C star to the R to C star, well, that the set of all such homomorphisms, it's naturally isomorphic to Z to the R. And that copy of Z to the R sits physically inside H star. So we have a natural copy of Z to the R in C to the R star, the dual space of C to the R. And so if I take this lattice and take its real span, that is a real form of H star, real infinitesimal character means chi lambda with lambda in its real subspace. And why this is so, why this is a distinguished space of reducible Harshanga modules with such infinitesimal characters, that I will explain in the third lecture. Okay, that's enough for today.
Thank you very much. Anybody would like to say something, ask a question, or comment, please?
Well, somebody must have some questions.
I have a question.
was just curious, you were concerned that space HC of D is incomplete. Can you elaborate on your concern?
No, I guess, so it's a function from something to something.
Yes?
And the definition of the representation, it was on a complete Hausdorff topological vector space.
Yes?
So it's a function from one category to another. It's just you change categories at this point.
Yes, it goes to the category of our Shannon model, yes, nothing wrong with that. But I mean, then, of course, there was the statement that these are analytic vectors. The analytic vectors, when we think of them, actually as physically sitting inside this on the vector.
So, you were just making a remark.
Yeah,
It's not a...
Okay, further questions?
When do you lift the restriction on the who ask questions?
Now you can ask questions.
I'm curious, I realize you gotta talk about this on just as a hint. What do you mean that people have given a description of the irreducible Varsham moments? That's what I understood from your talk. So
You have a very fine hearing there.
yeah. So then the question is, in what sense is that a description? You're describing modules as sub-modules of modules that are constructed geometrically.
Yes.
But the sub-modules, do they, in your mind, do they have a geometrical?
Of course.
And the geometry comes from,
The geometry of K-orbit.
so the K-orbit is picking out a unique.
For the K orbit, you get the standard module.
Yes.
And then on each boundary piece, you can ask whether that boundary piece induces a potential restriction a potential that you might be able to restrict the E module in some geometric sense to the sub-module, to the suborbit,
Yes.
the orbit enclosure. When you can, then all the ones that restrict regularly to that orbit, that gives you a submodule. And if you look at all the boundary orbits, take all of the conditions that you get from those, that gives you the irreducible submodule. So let's say on the case of P1, you can look at each of the two point orbits of K, and you're going to ask, do you have a singularity there or don't you? If you don't have a singularity, that restricts the module, and you look at those which don't have singularity. I thought that's completely analogous. Again, completely analogous, not as explicit, but
Okay.
well, it's pretty explicit.
Is it explicit in the sense of an algorithm? If you wanted to know the answer in a particular case?
Well, I mean, asked me in the third lecture. So, I mean, there certainly are answers. I mean, it's just that, maybe so there are different ways of putting the answer. One way would so we have, typically we have parameters. Right? I mean, so for the discrete series, yes, so of course I should be careful. Namely, I always look at the dominant ways, so that, there's no higher bound. So then for the closed orbit, these things are irreducible. I mean, there is no reducibility condition at all. So now if you don't have a closed orbit, then you always have parameters. And you can ask, and so you can ask for reducibility with respect to, where this occurs for the parameter. And then you can ask for a single reducibility, right? Just with respect to one of the roots. And that you can describe geometrically. And then the general case is simply you take the closures of all of those conditions. That's pretty explicit.
You're talking about this more on.
Well, there is this paper of 4 authors, which was never, it should be finished, but never was. That's discussed in there. Look at this.
Two of the authors are here, so I can keep on this.
Yes, you can.
We're learning more about these papers. I've heard from some missing authors in these papers. Okay, any further comments?
Maybe I could ask, so -2 is the true number of the canonical power.
That's correct.
And if we have an invariant form, volume form, we need that for the discussion, actually, because you're talking about L2.
Yes.
And then we have the canonically associated metric on the canonical power, and we have the same thing, but it might be mixed signature. In general.
In general.
Say for fragment or something.
If you look with respect to the wheel. Yes. So you see, and so the question he was asking was realizing representations geometrically in the flat variety, and there are two dual pictures. I will talk only about one, namely you can look at the K orbits and the GR orbits. On the side of the GR orbits, you actually see the representations. And on the K side, you see the Harshad models. And so this is really like, I wouldn't say gentle and high, because both of them are perfectly nice. But it's like, maybe like jumps. So it has 2 heads. And, you see certain things more easily on one side, certain things more easily on the other. And so for the GR side, which I'm not going to talk about, so the analog in general of what I described for SU11 is you look at the open orbits, let's say when you have a compact cut down. You look at the open orbits, and then everything I said makes sense. You can look at the open orbit. You have line bundles, they have a GR invariant emission metric. There is a GR invariant emission metric on the more than one, but the natural one on the orbit. And then you can look at the L2 holomorphic forms that are L2. And somebody who did this a long time ago was Harshad. And Harshad usually didn't make mistakes. But there is one really big mistake of Harshad on the record, namely in the proceedings of the Amsterdam Congress, which was, I think, in 1954, where he said, if you look at L2 holomorphic sections of these line models, so that's not the language he used. That is precisely the discrete zeros. And of course, the answer is absolutely not. So square integral holomorphic sections that you would not expect except in the emission symmetric case. And so in general, instead of L2 holomorphic forms, you look at L2 cohomology. But then you get all of the discrete zeros that way. In terms of L2. And that's how I started out.
But is enough philosophically because the correct metrics on these things are mixed signature metrics?
Absolutely.
Yes.
No, I can even tell you a little more about this.
Of course, I thought
so. I was a graduate student at Berkeley, and my advisor was Griffiths, and he was looking at these classifying spaces of Hodge structures. And Langers was visiting at the time, and Langers was thinking about the discrete series. I think he talked to Harshchandra. The question was how to actually describe it geometrically, or in any way. Harshchandra described the characters, but never written down a vector space. And so then Griffiths had calculated the signatures of these spaces, and Griffiths said that
What do you mean signatures?
of the emission forms,
Of the
of the metrics.
Of the metrics that appear now.
Yes, yeah. And so then he said something which from his point of view was obvious. Namely, on a compact manifold, the Qaisar vanishing theorem, and what you look for is precisely the signature. And then, more generally, on a compact manifold, roughly speaking, so to get the precise statement is trickier, is that the signature tells you in which degree you expect or not. And then, if you think analytic geometrically, then the analog for non-compact manifold is obvious. That you should expect not holomorphic sections when you have mixed signature, but L2 homology in different degrees. And so this was obvious to, that's how it ought to go. It was obvious to Griffiths. And then Langlands actually formally wrote this as a conjecture. And that was my thesis project, which I did not solve for my thesis. I did this slightly later, but actually what I did in my thesis in some sense was, in retrospect, even more important.
So, but I just wanted to check, since you're not going to talk about this,
Yes.
and you're an expert, we start with invariant volume form.
Yes.
We have something, I don't know, Kozul calls it a canonically associated Hermitian metric on the tangent bundle. You look at this on the canonical bundle. This somehow is in the center of this discussion.
No, so first of all, let me say what the obvious emission form is, because that's not entirely obvious.
Okay.
So the natural emission form is, so if GR is compact, then there's an obvious one, right? And you just take this by change of scale, it's the same one. So it's a Kähler form. And there's more than one metric, but there's a good one and an obvious one to take, which becomes the obvious one when.
Yeah, but that's not a complete metric or anything on reflector.
Yes, it's in there, it's not.
It's not complete, it exists on the end of the
Yes, that's correct. Well, no, actually, so of course, it's on GR not the contact are done. So it exists just in the open world.
Well, then I didn't understand what you were saying. So, good.
It exists on GR, not the TR.
Yeah.
And so, yes, it can be complete.
You're not talking about the pseudo-Kähler form.
Yes.
That exists too. So,
that's what I was saying.
yeah, of course, in the end, it doesn't really matter. But I think if you want to look at L2 cohomology, you should look at the positive definition. So you should talk about
that was my question.
Yeah. You should look at a positive definite one because you want the overset.
Right.
At one time, we were looking at the pseudo-Kähler.
Right.
Well, I was looking at that too, of course.
Okay, I would.
So in that case, how do you unitorize the cohomology? Say for both cohomologies.
Well, you have Hermitian metrics, positive definite metrics. And so you look at L2 forms whose derivatives are L2. Then you can look at a complex. The L2 homology is the homology of a complex.
Okay, I would say the following. I don't know. So, first of all, I'm very pleased with the way this lecture is going, in the sense of, the level, and I think this exactly what we need. And I don't know how far you're in your plan, but feel free to take more time in the other 2 lectures so that you can exactly cover what you intend. So,
Yes, I mean, I will adjust at the appropriate points.
yeah, but don't get it short, because we're not getting tired of this. This is going so well, and then so well, so we don't want to.
Yes, I should say the next lecture will be totally different. It will be much different.
So thank you very much.